The objective of this video is to establish a model for stator current as an equivalent surface current density. You'll see that I've sketched on here a cross-section for an electric machine, and I've just sketched a portion of the stator. So we've got the stator out here, and we've got a rotor in the center. And we're not too concerned about what that rotor looks like. It could be a permanent magnet rotor, it could be an induction motor rotor, doesn't really matter. And inside our stator slots, we have some conductors. In fact, we have ZQ conductors within a slot, and each conductor is carrying a current of I. Recently in our videos, we've been considering the stator to have a nearly infinite permeability, or rather we've been considering our iron regions to have a nearly infinite permeability, and we'll do that again. And remember that this assumption is due to the fact that if we have unsaturated steel, our air gap permeability is so much lower than the steel permeability that for most of our analytic modeling purposes we can consider the steel to have a permeability of infinity. And what this means is that the H field in our iron regions is approximately 0, so that our entire stator surface and rotor surface become equipotential. And we'll assume that there is a certain air gap between our rotor and our stator, and that air gap will be delta. So under these set of assumptions, what we're going to show in this video is that you can model your stator slot current as being an effective surface current density sitting on the inner bore of a slotless stator. Now, why would you want to do this? Well, it turns out that this greatly simplifies our calculation of fields in the air gap, and that allows us to study complex winding structures. We'll be developing tools to study windings based on the equivalent surface current density over the next set of videos. So when we go to calculate the magnetic field in our air gap, we do it by evaluating Ampere's law. And in this case, we're going to pick our Amperian loop intelligently to go around this first slot's conductors. So if we pick an Amperian loop that takes this path here, and it doesn't matter precisely where we cross on the tooth surface because the entire surface of the tooth is equipotential. So we could have chosen to cross over here, and it would have been the same as where we're currently crossing. And so at each portion of the Amperian loop, we have different values of the H field, which we're going to assume are constant with the length. So at alpha 1, at angle alpha 1, we have H of alpha 1. And this is specifically the normal component that we're talking about, the component that travels radially across the air gap. We're assuming that it does not vary with the air gap length, so it's the same H field right at the rotor surface as it is right at the stator tooth surface. And above, we have H at alpha 2. And then, of course, in the iron regions, H is 0. So when we evaluate the integral of H dot dl over this red loop, we get it equal to the integration of J flowing through that surface, which is just going to be our total number of slots times the current flowing in that slot. And because we've made this assumption that the H field does not vary with the air gap length, we can easily evaluate this closed loop integral as the following. Notice that we have a negative H at alpha 2 because of the direction that's indicated on the Amperian loop. The path dot dl is pointing inwards towards the rotor, so that reverses the sign of our radial field component. Okay, so we've got this expression for the total current that is linking our path here. Given these assumptions, we could draw an equivalent machine that has a surface current density on the inner bore of the stator as follows, where we've divided the total slot current, ZQI, by the angular span of the slot opening. So if we call this angular span here alpha 0, we can see that there's a surface current density on the inner bore of our stator at that location. And if we were to resketch our Amperian loop, we would end up getting the exact same calculation for our field quantities. Instead of calculating the total current enclosed in that Amperian loop as being the integral of J dot ds, we would be instead talking about the total current as being the line integral over the slot opening. And in fact, we can take this further. We can start to shrink our slot opening down until our equivalent model has just a single point of current located at the center of our slot opening with a total value of ZQI current flowing through it. And again, this surface current density is occurring at the center of the slot opening. So this point right here maps to where this is occurring. We can summarize this as that we have defined an equivalent circumferential current density. This is a surface current density that is expressed as a function of alpha, the circumferential direction. So we define an equivalent circumferential current density on the inner bore of the stator, such that AC of alpha, the subscript C is for circumferential, AC of alpha is equal to the total slot current when alpha is at the center of the slot, or it's 0. So our circumferential current is going to be 0 all along up here, and then all of a sudden, when we're at the center of a slot, it's going to have the value of the total number of ampere turns in that slot. And why do we do this? Well, again, we do this because it ends up being a useful tool for studying the fields created by a complex winding. So in summary, this short video has introduced the concept of an equivalent surface current density so that we can take our total slot shape and structure and model it as a single point of current in the inner bore of our stator. And the reason that this works is that we are assuming that our iron regions have nearly infinite permeability, and therefore the H field is 0 in the iron, and we have these equal potential surfaces. And when we do this, we get this simple expression for where our current density is located, and this enables us to consider complicated winding structures, which you will see over the next sequence of videos.